Namaskar, welcome to the channel Anka Ananda Aharan, that is extracting happiness from the teaching learning process of mathematics. Today we will discuss about projections and least squares. Before going for it, let us study what's the need of doing this study. Suppose I have a vector A and I have x is equal to b. It has, so here a vector into x is equal to b. It has solution only when, if and only if, that is if and only if b is a scalar multiple of a for some scalar c. Otherwise it has no solution. But consider 1, 2, 3 into x is equal to 1, 0, 1. So here what is a? This is a, this is b. Now clearly it can be felt that b is not a scalar multiple of a. So that means this system of equation has no solution. So what I have to do? I have to replace my b vector by a vector p which is a scalar multiple of a. So what I have to do? I have to find out, this is my b, it is given, it is my a given. Now what I will do? I want a vector of a vector p which is along a and which is having minimum error with b. So this is my p vector which is along a, and this is the difference, it is error, sorry, this is error e is equal to, it is e is equal to b minus p. This is my error vector. Okay, so what is error? Error e is equal to b minus p. Now, under what condition this error will be least? Suppose I have like this. Suppose I have this vector like this. This is like, these are different projections of b along a. Now, which projection is having error part minimum? If I am projecting it orthogonally. So, if B is an orthogonal projection, if if I am projecting B orthogonally onto A, then my error is least. So, that orthogonal projection we are interested to find out. What's the meaning of orthogonality? Here the error must be orthogonal to A to have least value or least length. So what is our target then? To find P with square of length of E, least square is least with this. And this is possible if and only if E is orthogonal to A or A is orthogonal to E, they are same meaning. That implies and implied by A transpose E is equal to 0. We will discuss further regarding this. Now let us discuss about P and A. So P is a scalar. What is my target? My target is to find out a projection vector P which is a scalar multiple of A and with least square of the error least. So least square by using least square method. So let, as P is a scalar multiple of A, let P is equal to, that scalar is x cap and A. So our target is to find out x cap. So let us substitute. So here this is, it is A transpose E means B minus P. P is X cap A. That implies this is equal to 0. That implies A transpose B minus X cap. Because it is a constant, I can take outside. Otherwise, it is a not much issue. So it is 0. So what is my X cap? Here my X cap is A transpose B by A transpose A. I am writing in the denominator because it is a scalar quantity. Okay, inner product of two vectors is a scalar quantity. So this is my X cap. Once I got my X cap, what I require? I require my P. What is my P? P is equal to A. This is my P. A transpose B by A transpose A. That is AX cap. It is my formula for P. It is projection vector P. What is this P? This is, here P is projection vector from B along A. This is my small p. Now this small p also I can write like this. How I can write? A transpose B. Here previously the bracket was there. Now I will make it a bracket like this. And I will divide it by A transpose A as it is. So here this is a matrix. This is a matrix. And this is a scalar. So matrix by a scalar means it is a matrix. So this is P into B. So this P is equal to A transpose by A transpose A, which is, what is its target? Its name is projection matrix. What is its role? Its role is to project. It projects any vector B along A to get P is equal to PB. That means I have to multiply B with P to get the projection of B. If I want to get projection of C, then I will write PC. If I want the projection of D, I write PD. So likewise, any vector whose projection along A is to be obtained, simply that vector is to be multiplied with the P. So P gives the projection of any given vector along or onto A. So here this is my projection matrix. Next is, all these things we have done in the previous video to some extent. So now we will extend it to a system of equation. There only one vector we have considered. Okay, suppose I have a matrix equation AX is equal to B. It has solution if and only if B belongs to C of A. If B does not belong to C of A, then it has no solution. Okay, but in reality, in most of the cases, B does not belong to A. Let B does not belong to C of A. That implies AX is equal to B has no solution. But as it is a real life problem, I cannot simply avoid by telling that it has no solution. We have to find out some solution because it is real life problem. So in this case, we will find out an approximate solution. First, to find this approximate solution, we will first approximate B by a vector in C of A. So I will find out a vector in C of A which is having least error with B. So what is my target then? So what I will do? Let that vector is P. Let P belongs to C of A be the closest approximation, best approximation of B in C of A. So then what it is possible? So that means it is best approximation means square of the error is least, that is E square is least. And when the error will be least, what is error? When the error will be least, if my projection is orthogonal, if B minus P, that is projection, that error is orthogonal to C of A, this is least if and only if E is orthogonal to C of A. E is orthogonal to C of A. What does it mean? It means E belongs to N of A transpose. We'll continue this process, but before that, let me explain few more steps. So now what we have taken? We have taken P is a vector in C of A which is orthogonal projection. This is orthogonal projection of B onto C of A, column space of A. So now as this P belongs to C of A, AX is equal to P has solution. But it has solution. Can it be the solution original? No, original X, it is not the original X. It is a best fit solution. Its name we will give as X cap. So here X cap is the best fit solution and it is the solution of AX is equal to P. X, that is AX cap is equal to P, and it is different from X. And the error is least. With that, I have my X cap. So now what is my B? B is original vector. What is my error? Error is equal to B minus P. That is B minus, what is my P? A X cap. So here X cap is the solution vector. So it is a vector. In the previous article, X cap was a scalar. Now onwards, this X cap is a vector quantity. It is an approximation to the solution vector. So it is best fit solution to the system of equation. Okay. So now with this formula, we will substitute here. So this implies when a vector belongs to N of A transpose, it implies implied by A transpose E is equal to 0. That implies and implied by what is E value? It is B minus A X cap. It is P, it is B is equal to 0. That implies and implied by A transpose B minus A transpose A into X cap, or this is equal to this, which is our normal form. Our normal form equation is exactly A transpose A x cap is equal to A transpose B. It is said to be normal form equation. Okay, from here, what is my x cap? These are matrices. I will not divide. I will find out inverse. So A transpose A whole inverse A transpose B. This is one of the significant formula for the best fit solution to the given system of equation. If only at solution level the question is completed, then we should find out only x and stop there. Suppose I want the projection matrix also, projection vector also. What is my projection vector? A x cap. Then what will be its formula? This implies P is equal to A transpose A whole inverse A transpose B. This is my projection vector of P, which is projected from B onto C of A, out of which this is again another matrix. This matrix is multiplied with B to give P. That means this matrix is nothing but my projection matrix PB. So from here, this is projection vector, it is projection matrix. Projection vector is the vector projection of B onto C of A, and projection matrix is the matrix which projects any vector B onto C of A. So here clearly what is my P matrix? It is this part, that is A transpose A whole inverse A transpose. So this is projection matrix. Now you multiply any vector B with P, we will get the projection of B onto column space of A. So this is my P. Now this P also satisfies those two conditions, that is it is symmetric, P transpose is equal to P, and also P square is equal to P. Let us verify. P transpose is equal to A transpose B A whole inverse A transpose. Okay, it's a whole transpose. So we know A B C whole transpose is A B C whole transpose is nothing but C transpose B transpose A transpose. A transpose. So applying that property, first I will write it is nothing but A transpose transpose. Then it is A transpose inverse is equal to A inverse transpose. So there is just no issue if I am taking the transpose inside the inverse symbol, as A inverse transpose is equal to A transpose inverse. So there is no issue. This is already known to us. Using this, I can take my transpose inside this, that is it's a transpose whole inverse, then it is A transpose. So let us substitute the property what it is. A transpose is A, and what about its transpose? It is A transpose A whole inverse. It is A transpose. Again we got P. So P transpose is equal to P implies P is symmetric. P is a symmetric matrix. Okay, what is next part we want to do? That is P square is equal to P. This we want to prove. So what is P square? A A transpose A whole inverse A transpose, this is P, into A transpose A whole inverse into A transpose. This, how much it is? This is this and this considered together. How much it is? It is, this is equal to A. This A something inverse into something is identity. So AI, then it is A transpose A whole inverse A transpose. How much it is? A transpose A whole inverse. It is A transpose. This is nothing but P. So we started with P square and we ended with P. So that implies it is proved. We wanted to prove it and it is proved. So what is expected? Suppose I'm given with a system of equation where the B does not belong to C of A, so it has no solution. Then I am interested to find out a best fit solution of it, or best approximation or best estimate of this, or of this solution. Then I will find out x cap using the formula. This is my best fit solution to the given system of equation, or least square method solution of the given system of equation, which is nothing but A transpose A whole inverse A transpose B. Using this formula, I will find out the solution. Suppose in the exam it is asked, or suppose somebody is asking me, find the projection of B onto the column space of A. Then simply that projection I will write P is equal to A x cap. So here in place of x cap I write this much. Suppose I am interested to get the projection matrix, or any property of a projection matrix is to be used. Then I will find out my projection matrix, which is nothing but capital P is equal to A transpose A whole inverse A transpose. These are the issues, and where the projection matrix satisfies these two conditions already we have verified. So now the target is fitting fitting a data to a straight line by least square method. Suppose I have a set of, suppose we do a series of experiments and expect the output B to be a linear function of input T. That is, B is a linear combination, a linear function of the function. That is, B is equal to C plus dt. This we want. Now let us, so we have conducted experiment. For T1 value, I am getting the component B1. For T2 value, I am getting B2. So similarly for Tm value, I am getting my Bm. So putting the value of T1, T2, T3 up to Tm, we are getting this system of equation. Now the system of equation, observe here, in everywhere the first component is only C. So if I take, so here I am fitting a straight line, that means I am obtaining this C as well as D. If I got these two, that means I got the straight line. So these are the two unknown variables which I want. But directly it has no solution. So we will find out approximate solution of C and D. Let us verify. If it has solution, then also what to do. If it has no solution, then also what to do. So this system of equation where C and D are the unknowns, I can write it as, so the coefficient of C in every equation is 1. Coefficient of coefficient of D is T1, T2, T3, like this. So if I write this system of equation as a matrix form, as in matrix form, so this is my A, this is my X, this is my B. So this is AX, is equal to B. So here one can observe this method we will use only when my first column is 1. Each element in the first column is 1, then only this method can be useful. Okay, this method actually originally it is useful for any, but in particular because I am fitting a straight line, so whatever we will discuss now, they are only when it is fitting a straight line. So I am interested to find out C and D. So here the first components of this coefficient matrix are all 1. Now what about each term? Original expected value is B1 and I got my value C plus DT1. So what is the error component? This B1 minus C minus DT1. Similarly, what will so here what is the error? E is equal to its vector. It's a vector. How much it is? It is B1 minus C minus DT1. B2 minus C minus DT2 and so on. Okay, it is Bm minus C minus DTm. So this is my error vector, and error vector's length square is each component square. So each component square's sum is the length square. So this length square, length of the error, its square is least for what value of C and D that is to be verified. Here also we can use calculus to find out C and D. What calculus, what are the concepts? Observe every function is a function of C and D. So if we find out dou E square by dou C and equal to 0, we will be getting extreme value. Simplifying or solving it for C, we will get value C. Similarly, another equation is dou square. This is length. Okay, it is not E square, it is length by dou D is equal to 0. From these two equations, we will find out C and D and substitute in the equation that B is equal to C plus dt. This value and this value we can substitute. So to get our best fit straight line to the given data. This is using calculus method. But in case of linear algebra, we will go for least square method. That is what it is. What we will do? Our E is least. Square of E is least. E square is least. If and only if E vector is orthogonal to where it is to be projected, column space of A. When B vector is projected onto the column space of A, if E is orthogonal to the column space of A, then my E is square of E, length of square of E, square of length of E is least. So this implies what? Already we have derived all those things. So that is E belongs to N of A transpose. Then finally we got it. Already we have proved it. This part. So now what we will do in this case, while fitting a straight line, not much task is left. So observe here, directly what I will get, what is my x cap? X cap is A transpose A whole inverse, or from normal equation we will write. Okay, what is normal equation? It is A transpose A into X is equal to A transpose B. So here what is A transpose A? Simply, what is A transpose A? It is nothing but 1, 1, 1, A column. First is in terms in this format. 1, 1, 1, all this will be 1. And it is T1, T2, T3, Tm into 1, 1, 1, T1, T2, T3, Tm. So what we are getting in the examination, all these things are not necessary. That's why we will have some fun. So here what is to be done? 1 into 1 plus 2 into 1 into 1, 1 into 1. So m times I am adding 1. So it is m. Then 1 into T1 plus 1 into T2 plus 1 into T3, that is, it is sum over Ti, I is equal to 1 to m. Again T1 into 1, T2 into 1, all of them are added. So it is again I is equal to 1 to m sum over Ti. Then it is again, it is T1 square plus T2 square plus T3 square. So it is sum over Ti square, I is equal to 1 to n. So this matrix, this is my A transpose A. Similarly, what is my A transpose B? A transpose B, it is 1, 1, 1, T1, T2, Tm. It is B1, B2, Bm. It is how much? 2 into m, m into 1. The resultant will be 2 into 1. 2 rows, 1 column. What is the first row? B1 plus B2 plus B3 and so on. Sum over Bi, I is equal to 1 to m. The second is sum over Ti, Bi, I varies from 1 to n. So in the examination, if fitting a straight line question is asked, what is expected to be done? I need not calculate much. So from directly my data will be for this Ti, this Bi is there. Matlab 1 T1 is equal to 1 T, for T1, T2, T3 it will be given. Similarly B1, B2, B3 it will be given. Only this much will be given and directly I can find out my X cap. What is it? C cap, D cap. Or CD directly we can also consider it as. Okay. So it can be considered as a CD. What it is? This is nothing but from this equation, it is nothing but A transpose A whole inverse A transpose B. So this is M. Directly in the exam we can go for it. Sum over Ti, sum over Ti, sum over Ti square whole inverse sum over Bi, sum over Ti Bi. Directly in this formula we can put the data and we can get our answer. We need not write much. Simply this much is sufficient. So here also we know one of the formula that A, B, C, D. To find out the inverse also we need not do much. What it is? AD minus BC whole into DA minus B minus C. This is the inverse. Using this property, this inverse can be calculated. This can be calculated. So within one or two steps, directly we will get our x hat. Then what is to be written? Then either b is equal to or y is equal to c plus dt. So here c value we have to substitute, d value we have to substitute. This is the linear equation. Here in if required we can write b or we can require y. Usually b is, we used to take as a constant vector, so that's why it is better to write y. So here y is a variable, t is a variable, t is independent variable, y is dependent variable. So with this we can fit any straight line to a given data in a simplified manner. We need not go for much complicated information. Where are the formula? So with this, our theoretical aspects of orthogonality are being completed or done. In the next video, we will apply the concepts of chapter 2 and chapter 3 together to solve all the problems of most of the problems of chapter 2 and chapter 3 because they are interrelated. Now, thank you for your patient listening.